Good morning, everybody. Today we will be learning about temperature inversion. Temperature inversion. In this, we will be looking into five aspects. The first is the definitions, definition of what do you mean by normal lapse rate and what do you mean by the temperature inversion itself. The second thing that we will be looking into is the types of temperature inversion. Basically, there are two types. One is the surface inversion, and the second one is the upper air inversion. Surface inversion and upper air inversion. We will be looking into the difference between these two types of inversion. Okay. The third thing that we will be looking is the subtypes of these two inversion. The surface inversion has three subtypes. The first one is the radiation inversion. It has three subtypes. It has three subtypes. The first one is the radiation inversion. The second one is the air drainage inversion. And the third one is the advection inversion. We will be looking into detail all the three subtypes of inversion. The upper air inversion, it has two subtypes. The first one is the subsidence inversion and the second one is the frontal inversion. Subsidence inversion and frontal inversion. I'll be explaining you all these five subtypes in detail with the help of diagram. The fourth aspect that we will be looking is the significance of temperature inversion, the importance of temperature inversion. It helps us in study of formation of fogs and all. Significance of temperature inversion. And the last point that we will be covering is the atmospheric stability and instability. This is very crucial point, important with respect to your mains. Atmospheric stability and instability. It is in relation with temperature inversion. That's why we will be covering this at the last. So let's begin with the definitions. The first one is the normal lapse rate. Normal lapse rate. Now, as you move higher from the ground surface, that is, as the altitude goes on increasing, you will observe that the temperature goes on decreasing. This phenomenon is observed almost at all the places over the Earth's surface. The temperature decreases at an average rate of 6.5 degrees Celsius per kilometer. As you move higher in the altitude, the temperature decreases at an average rate of 6.5 degrees Celsius per kilometer. This is called as the normal lapse rate. So the definition of normal lapse rate is the rate of decrease of temperature with increasing altitude. Sorry, the average rate of decrease in temperature with increasing altitude at an average rate of 6.5 degrees Celsius per kilometer is called as the normal lapse rate. The second thing is, what do you mean by temperature inversion? Now, what happens is at certain places during certain seasons, this normal phenomena is not observed. At certain places in certain seasons, what happens is as you move higher in the altitude, the temperature instead of decreasing, it goes on increasing. This increase in temperature with increase in altitude is referred to as temperature inversion. So, the definition of temperature inversion is the rate of increase in temperature with increasing altitude is referred to as temperature inversion. Okay? I hope this is clear. When we are studying about temperature inversion, we will be sticking only with respect to troposphere. You all have studied about the vertical profile of the atmosphere. There is troposphere, stratosphere, mesosphere, and thermosphere. Okay. When we study temperature inversion phenomenon, we study it only with respect to the troposphere. Because most of the environmental activities, most of the presence of atmosphere is it lies within the troposphere. The stratosphere is a zone of permanent temperature inversion. Now, what do you mean by this? Let's say this is the Earth's surface. This is troposphere. It's the extent of troposphere is somewhere around 20 kilometer. Then there is stratosphere up to 50 kilometer. In the stratosphere, due to presence of ozone layer, there is reflection of UV light, and as a result, this entire portion, the entire portion in the stratosphere gets heated. So as you're moving higher, the temperature goes on decreasing up to troposphere. It remains stable in tropopause, and then it again goes on. Sorry. It decreases, remains stable for some, then it increases again. So if you look here in the stratosphere, there will be always increase in temperature with increasing altitude. It is because of the presence of ozone layer and reflection of the UV rays. As a result, in the stratosphere, the temperature increases with increasing altitude, which is referred to as temperature inversion. But this zone is a zone of permanent temperature inversion. But in the troposphere, it the phenomenon of temperature inversion varies at different places in different seasons. So we will be studying the phenomena basically in the troposphere itself. Let's understand temperature inversion with the help of diagram. Now this is the diagram of temperature inversion. Is everyone able to view it? दिख रहा है सबको? ठीक है. So here you can see this. If you see this dotted line over here, this is the normal lapse rate. As the height goes on increasing, as the altitude, the elevation goes on increasing, the temperature is decreasing at a steady average rate. This is called as the normal lapse rate. But at certain places, during certain seasons, there is increase in temperature with increase in height. Here you can see the temperature is increasing. It increases up to certain elevation, then it again goes on decreasing. All this will be covered in detail in upcoming part, but for time being, just understand that up to certain elevation or certain height, certain altitude, the temperature goes on increasing with increasing height. This concept is called as the temperature inversion. I hope this is clear to all of you. Or should I explain with one more diagram? In normal conditions, this is elevation, temperature. In normal conditions, there is warm air mass along the ground surface. There is cold air mass at certain elevation. So in normal condition, what happens is the temperature goes on decreasing as you move higher. Okay, this is the normal situation. But in case of temperature inversion, this is temperature, this is here, it is elevation. In case of temperature inversion, what happens is there is cold air mass present along the ground surface. It happens in particular seasons only. I'll be talking into detail when and where it actually happens, when we'll be looking into the types and subtypes. Okay, there is cold air mass, above it lies the warm air mass, due to which the temperature goes on increasing with increasing altitude. This is called as the temperature inversion. Okay, now if you all want to draw this diagram, you can just note it down. Now let's move ahead. We'll be talking about the second point, that is the types of temperature inversion. Okay. As I said initially, basically there are two types of temperature inversion. One is the surface inversion and the second one is the upper air inversion. In surface inversion, the inversion of temperature begins right from the ground surface, right from the surface of the earth. That is why it is referred to as the surface inversion. In surface inversion, the increase in temperature with increase in height begins from the surface itself. That's why it is referred to as the surface inversion. Surface temperature inversion. Surface temperature inversion. Here, the temperature inversion begins right from the surface of the earth. Okay. The second type is the upper air inversion. In upper air inversion, the inversion in temperature starts at a certain height, certain elevation, or certain altitude. For example, second subtype, upper air inversion. In upper air inversion, this is temperature, this is elevation, altitude. Okay. The temperature goes on decreasing with increase in altitude up to a certain height in the troposphere. I'm talking about troposphere only, in the troposphere itself. But after reaching certain height, it goes on decreasing. Okay. So here you can observe it usually happens at somewhere around, let's say, somewhere around 600 to 1000 feet. At this, from this height onward, the temperature goes on increasing. So this is called as the upper air inversion. Okay. I hope the difference is clear. Any questions, any doubts up till now? In geography, there is nothing specific or nothing ideal conditions as such. Okay. Most of the time, the things, the climate, the weather, it keeps on changing. It's highly dynamic. It's highly dynamic. So don't make some rigid thoughts in your mind regarding this thing that this will happen all the time. Okay. These are some basic climatic and weather phenomenon. Okay. So let's move ahead with our third part, that is the subtypes of these two temperature inversions. The first, the three subtypes of surface air inversion. Surface inversion, surface inversion, surface temperature inversion. The first subtype is the radiation temperature inversion. Radiation temperature inversion. The major source of heating of the atmosphere, the major heat source of the atmospheric layers above the Earth's surface is the radiations emitted, reflected back from the Earth's surface. Okay, so the layers of the atmosphere along the Earth's surface, it gets heated due to the radiations reflected from the Earth surface. The Earth's surface gets heated due to the incoming incoming solar radiation, which ultimately heats the atmospheric layers above the Earth's surface. But at certain places, in certain seasons, what happens is, especially during long winter nights, the outgoing radiation, this outgoing radiation is much higher. This outgoing radiation is much higher than the incoming solar radiation during winter months. Due to the long winter nights, the solar radiation received by the Earth's surface, due to the less duration of day, the incoming solar radiation is less and the outgoing radiation is high, due to which the Earth's surface, the Earth's surface, just like any other objects which become cool during nights, the Earth's surface also cools rapidly, and the layers near the Earth's surface acquires the temperature characteristics of the Earth's surface, and thus the layers of the atmosphere also cools down. During long winter nights, the Earth's surface cools down rapidly due to the large amount of outgoing radiation as compared to the less amount of incoming radiation, and thus the layers of the atmosphere above also cools rapidly. Since the layers near the earth's surface cools down, but at as we go higher it is still little bit warm. It is little bit warm as you go higher. As a result, the temperature goes on increasing as you move higher in the altitude. So, in radiation temperature inversion, which occurs under certain ideal conditions, the temperature goes on increasing as you move higher in the altitude. It is referred to as the radiation temperature inversion. There are certain conditions which favor radiation type of inversion. Okay, let's look into the ideal conditions during which the radiation temperature inversion will occur. The conditions that favor radiation inversion are: the first one is the long duration of winter nights. Okay, long duration of winter nights, because as just now we saw, the outgoing radiation is much higher than the incoming radiation during long winter nights, which facilitates radiation temperature inversion. The first is long winter nights. The second condition is the cloudless sky, or the sky with higher clouds. Higher clouds are called as the cirrus clouds, which are very thin. Cloudless cloudless sky. Now let's understand with the help of a diagram. This is the surface of the earth. If there is presence of clouds in the sky, what will happen? If there is presence of clouds in the sky, what will happen? Anyone? Yes. The outgoing radiations will be blocked and reflected back towards the earth's surface. So some of the radiations is reflected back by the clouds. As a result, the phenomenon of temperature inversion won't be observed if there are presence of clouds in the sky. Mostly in northern part of India, you will find that the western disturbances bring some rainfall, which is useful for wheat cultivation. So what happens during winter? Suddenly you will find that some of the days are quite warm. Okay, it is basically due to the presence of clouds which are brought in by the western disturbances in the northern regions of India, which brings in precipitation. Okay, so as soon as the clouds move away, they pour in as in the form of rainfall, they pour in water. As soon as the clouds are gone, suddenly there will be a drop in temperature again along the earth's surface. Okay, and the phenomenon of temperature inversion will be observed again. Okay, so the presence of cloudless sky or clouds, higher clouds, is the one of the ideal condition for occurrence of radiation temperature inversion. You'll look into the different types of clouds. The higher clouds are cirrus clouds. They are very thin clouds. Okay, so we won't go into detail about the types of clouds right now, but just try to understand the higher clouds are present at a much higher height, somewhere around 20,000 feet or something. Okay, but such types of cumulus and other types of clouds, if they are present, then the radiation temperature inversion won't be observed. Okay, so now let's move on to the third condition, the limited humidity. Limited humidity. As you all know, water vapor is the most abundantly present greenhouse gas. Water vapor absorbs most of the radiations emitted from the earth's surface that keeps our earth's surface warm. Okay, in the troposphere there is huge presence of water vapor. So if the water vapor is present in large amount, then if the water vapor if there is lot of water vapor in the atmosphere near the earth's surface, then the outgoing radiations will be trapped here itself. Okay, which won't allow temperature inversion, the radiation temperature inversion phenomenon. Okay, the fourth condition, there's no space. You can write these 3 points so that I will erase and write the remaining conditions. Okay, I'll move. The fourth condition is the fourth condition is there shouldn't be any vertical mixing of the air of the radiations, as we have seen in second condition. When there are presence of clouds, the radiation emitted from the earth's surface will be reflected back, so there is vertical mixing. Okay, due to this vertical mixing, the radiation temperature inversion, the phenomenon of radiation temperature inversion won't be observed. Okay, and the final fifth condition is the surface itself. Okay, the surface, the earth surface, the type of earth surface. For example, uh, a earth surface covered with snow or desert sand. As you all know, the sand, if you have ever observed or ever felt, the sand, it heats quite quickly as well as it cools quite quickly. Okay, so especially in the desert regions, you'll find that during afternoon the sand gets heated at quite high level. Okay, it becomes very difficult to step your feet bare feet in the sand at that particular during daytime. But if you observe at the night time, it becomes quite cool. Similarly, when we talk about snow, when we talk about snow, snow is a bad conductor of heat. This is earth surface. If it is covered with snow, if it is covered with snow, ice, what happens? Snow, it, due to its albedo effect, it reflects it reflects all the incoming radiations. Okay, then any heat from the earth's surface, it is also not transferred to the layers, the upper layers of the snow. As a result, the surface over here is quite cold. Okay, the surface above the snow surface is quite cold, and whereas the layers above the are comparatively warmer, and the phenomenon of temperature inversion will be observed. Is this fine? Any doubts, Krishna? Fine. So the five ideal conditions for radiation inversion are presence of long duration of nights. The second one is the cloudless sky or clouds, higher clouds. The third one is the atmosphere, water vapor, less availability, less humidity. The fourth one is the absence of vertical mixing. And the fifth one is the land surfaces, the type of land surfaces. Okay, so that's it. with the radiation temperature inversion. Now let's move on to the second subtype of surface inversion. The second subtype is the second subtype of surface temperature inversion is the air drainage temperature inversion. Air drainage. This type of temperature inversion is observed in the mountain valley regions, in the mountainous valley region. Now let's understand it with the help of a diagram. During winter, especially in the mountainous region, what happens is during winter seasons, or let's first understand with the normal situation. In normal situation during daytime, the layers, the earth surface at the valley bottom gets heated, which heats the atmospheric layers above, and the warm air rises, and due to less density and expansion the warm air rises, whereas the cool denser air sinks. But during night time, due to the effect of radiation window, mark this word, radiation window, I'll explain this in a short while. Due to radiation window effect, the cool air at higher reaches of the mountain, it becomes dense and heavy, and it moves along the mountains. The colder air, dense, heavy, colder air, it moves along the surface of the mountains towards the valley bottom, just like the drainage system, river drainage system. The air drains over here towards the valley bottom, and as a result, it pushes the warm air, it pushes the warm air above it. This cold air, it pushes the warm air above, and as a result temperature inversion is observed in the mountain valley region. Okay, now how this occurs, let's understand in detail. Just now I said about radiation window. Radiation window. The mountainous region, the mountain tops at higher altitude, the atmospheric layers at higher altitude is quite sparse. Okay, it is sparse. So whatever the incoming radiation is received by the mountain tops, it escapes into the space quite rapidly. What is the function of a window? Window, घर की खिड़की, to allow easy passage of air, okay, ventilation. Just like that, the mountain tops acts as a window for the incoming and the outgoing radiations. Okay, so the mountain tops cools quite rapidly during winter nights. As a result, the air masses present at the mountain tops they become dense, they become cold, dense, heavy. As they become dense, cold, heavy, they begin to drain, they begin to sink along the mountain surfaces. They move along the mountain surfaces towards the valley bottom. Okay. These are the mountain tops. Here, the outgoing radiation due to the effect of radiation window is quite fast due to sparse atmospheric layers. As a result, the dense the air masses become dense, cold, dense, heavy, and it begins to move towards the valley bottom, which pushes the warm air present. It push it pushes the warm air present at the valley bottom upwards. Okay. Here the atmosphere is quite dense and there will be trapping of radiations. As a result, there will be presence of warm air masses at the valley bottom, cold air masses at the higher reaches of the mountains. Slowly and steadily during winter night, these move towards the valley bottom, pushing the cold air masses above. As a result, phenomenon of temperature inversion with decreasing phenomenon of temperature inversion with decrease in temperature with increase in altitude. Fine. Sorry, I said cold over here. The warm air is pushed upwards. Okay. Sorry for the mistake. Yeah. Now, due to this, what happens is the temperature at the valley bottom, the temperature at the valley bottom, it falls below freezing point. As a result, the crops over here suffers from frostbite. Okay. If you have gone to any mountainous places, any hilly regions, you'll observe that at most of the places, the houses, the farms, they are located along the slopes. They are located along the slopes of the mountains. Okay. So why this is so? Because they avoid the frostbite conditions, the frost conditions. Okay. So this is all about air drainage temperature inversion. The third subtype of surface inversion is the advection temperature inversion. Advection means the horizontal movement of air. The temperature inversion can occur due to the horizontal movement of air. Sometimes what happens is either the cold air mass advects the warm air mass or the warm air mass overlies the cold air mass, due to which the advection temperature inversion can occur. This type of temperature inversion is mostly observed in coastal areas. For example, the northeast coast of North America, due to the movement of cold Labrador current. This you'll learn in ocean currents. Ocean currents, there is cold Labrador current coming from the Arctic region. Cold Labrador ocean current. Cold Labrador. So this cold ocean current brings in cold air masses from the Arctic region. So the cold masses, when they reach North America, especially around the Newfoundland region, somewhere there you can just look into the map. Okay. So what happens is the land surface temperature being warm compared to the cold Labrador ocean current, there will be formation of fogs in this region. Dense fog will be formed in this region. You might would have seen in movies like the Pirates of the Caribbean, or even in the Titanic, which sank somewhere here. Okay, so there was presence of dense fog. Okay, it was basically due to the convergence of cold and warm air masses. Okay, this also happens in upper air inversion, but now we are sticking only to the surface temperature inversion. So right along the surface of this ocean floor, of this land surface of Newfoundland region, near the ocean surface, dense fogs are formed along the earth surface itself. This is warm air mass, this is cold ocean currents present over there, due to which the warm air mass moving, it will rise above. Warm air mass being less dense, and in expansionary stages it moves above the cold air mass. As a result, temperature inversion will be observed at this particular location. I hope this is clear. Fine. So we have seen all the three subtypes of surface temperature inversion. Which are those? The first one is the radiation inversion. The second one is the air drainage inversion. And the third one is the advection inversion. Now let's move ahead with the subtypes of upper air temperature inversion. There are basically two subtypes of upper air inversion. Upper air temperature inversion. Two subtypes. The first one is the subsidence temperature inversion. Let's understand this temperature inversion in detail. Being an upper air inversion, it occurs at a certain height from the ground surface, as I've explained earlier. When the subsidence of air takes place, it gets heated, it becomes warm, due to adiabatic heating. Suppose an air mass is present, it is subsiding. As it is subsiding, there will be some layer over here. Just assume there's a layer over here. As it is subsiding, it gets accumulated over here in this region. As it gets accumulated, it becomes dense over here, dense compact, due to which it gets heated. Fine. Due to adiabatic heating, it gets heated. As a result, the temperature in this particular region, it increases. In this type of upper air inversion, what happens is, let's assume this as the Earth's surface. This subsiding air is not able to reach the surface of the Earth. There will be some stable atmospheric layer present where this subsiding air mass gets accumulated and is dispersed away from here itself. This happens due to multiple phenomenon which we will be looking into our climatology chapters, topics which will be covered in future. But just for time being, just understand that there is some stable layer over here which obstructs the subsiding air mass further from further reaching the ground surface. As a result, there will be accumulation of this air mass in this particular region, causing adiabatic heating over here, and as a result, temperature inversion phenomenon can be observed over here. Initially, from the ground surface, the temperature goes on increasing, but as there is heating in this region, as there is heating in particular this region, it will begin, the temperature will begin to rise up to certain height, and again it goes on decreasing in the troposphere. Okay, such type of subsidence inversion is common in high pressure belt region. Okay, there is one type of subsidence inversion which is the trade wind inversion. Let's understand it in detail. Trade wind inversion, it basically takes place in the tropical region, mostly, more specifically from 10 to 30 degree latitude in the tropics. In tropical region, this is, let's assume equator, 0 degree, 10 degree, 20, 30 degree, 10, 30 degree. Now what happens in the tropics? As you all know, there is presence of trade winds moving along the surface, which rises along the equator and subsides in the high pressure belts along the 30 degree latitudes in both the hemisphere. As these trade winds, they rise above the equator, they become cold. Why they become cold? Can anyone explain? These trade winds, after rising up to a certain height along the equator, they become cool, they become cold. Can anyone explain over here? Why does it become cold? बताओ भाई बताओ. बताओ बताओ. Why? It does lose heat, but as we have seen earlier, the major source of the atmospheric layers above the ground surface, above the earth surface, is the radiation emitted by the earth surface. So as it the layers of the atmosphere over here will be warm due to radiations from the earth surface. As it is moving away from the earth surface, it will become cold, dense and heavy. And as you know, there's a lid above the troposphere, tropopause, which mostly restricts the further rising of air. As it becomes dense and heavy, it starts moving. We will study these wind patterns in detail later on. Okay, but just for time being, understand. Okay, it moves just below the tropopause and it subsides over the 30-degree latitude. But this air mass, it is not one single line. There are a thick layer of air mass that is moving. So as it is moving, as it goes on cooling, it begins to subside right from the above the 10 degree latitude, but the subsidence is little bit restricted, okay, as there is rising air masses from here. So this subsidence will go on continuing and ultimately reaching the earth's surface at around 30-degree latitude. So what happens here in this region, as it is subsiding and being pushed away due to adiabatic heating, a warm layer will be formed over here. And in this region, if you are moving above, the temperature goes on decreasing, but here a warm layer will be present and here it goes on increasing further. So from here, the subsidence inversion layer is formed in this particular region. This region is the subsidence inversion layer. This is a diagrammatic representation, but as you might be aware, the distance between two latitudinal degrees, let's say 10 to 11 degree, the approximate distance between one latitudinal degree is somewhere around approximately 70 kilometers. So you can just imagine it's a 70-kilometer distance, and we are talking about 10 to 30-degree latitudes. So it's almost around 1400 kilometer. Okay, so this, let's say there will be hundreds of kilometer of layer where adiabatic heating will be observed, and thus the subsidence inversion will be observed at a certain height in the upper layers. That's why a subtype of upper air temperature inversion. Is it clear to all of you? Is it fine? These are anti-trades. These are trades. Anti-trade winds. These are trade winds. It cools, it becomes dense, and then moves ahead and later on begins to subside as it cools because it loses its source of heat, which is the Earth's surface. The main source of heat of the atmosphere is the Earth's surface. So the atmospheric layers, as we move above, it cools and become dense, and later on it subsides. So this is about subsidence temperature inversion. Now let's move on to the second subtype of upper air inversion, that is the frontal inversion. Second subtype of upper air inversion is the frontal temperature inversion. Now let's understand what do you mean by fronts. Fronts are a sloping boundary formed due to convergence of two contrasting air masses. A sloping boundary formed due to convergence of two contrasting air masses. Suppose this is the Earth's surface. It is a sloping boundary. This is front. This is front. Sloping boundary formed due to the convergence of two contrasting air masses. Suppose this is a warm air mass. This is cold air mass. The warm air mass being lighter as it meets a cold front, cold air mass which is dense and heavy. What will happen? Oops. What will happen? This warm air mass will begin to rise over the cold air mass. And such type of a sloping boundary or a sloping front will be formed. Okay. Now, as this front is formed, there is warm air mass now present in this particular region. There is cold air mass present in this region. You'll find that as you're moving higher in the altitude, higher in height, the temperature is decreasing, but at a certain height, a warm air mass is present. As a result, the temperature due to this warm air mass will go on increasing. Elevation, temperature, so what is happening? It decreases from here at to certain height. After certain height, it goes on increasing. So in frontal inversion, this is all about frontal inversion. In frontal inversion, there is formation of front due to two convergent air masses. The cold, denser air mass, it pushes the warm air mass above and ultimately leading to formation of temperature inversion. Fine, that's it. So this is all about the different types of temperature inversion. So we have seen all the 5 types of temperature inversion, 5 subtypes. The two types, main basic two types are the surface inversion and the upper air inversion. The surface inversion has three subtypes: radiation inversion, air drainage inversion, and the advection inversion. The upper air inversion, two types, two subtypes: the subsidence inversion and the frontal inversion. They are upper air inversion because the temperature inversion begins to occur at a certain height, certain elevation, at a certain altitude above the ground surface. Okay, I hope it is clear up till now. Now we will be moving towards the fourth point of temperature inversion, that is the significance of temperature inversion. In significance of temperature inversion, the common surface inversion leads to formation of fogs, as we have seen in advection temperature inversion. It leads to formation of fogs in the temperate regions. We have seen along the coast of North America in the higher latitudes. Okay, these dense fog, it affects navigation, as we have seen that Titanic sank. Okay, then sorry, that was a bad example, but it affects navigation because of the dense fogs formed in those particular region. Okay, in urban and industrial areas, these fog get mixed up with the pollutants present in the air, which ultimately leads to formation of smog. As we have see, if you are aware of the 1952 smog in UK, which almost took the lives of almost around 50 to 52 people, somewhere around that. You can just check the facts about it, but I'm just aware that in 1952 there was some such incident. There was heavy loss of life due to smog. Then in nowadays we can see in Beijing, the highly industrial regions of China, plus in winter season, the North Indian plains itself, there is occurrence of smog. Okay, then the condition, ideal ideal condition for temperature inversion in the mountain valleys, we have seen there is condition of frost. Frost occurs in the mountain valleys, which affects the lives of people living in the valley region, as well as it affects the standing crops. Okay, then we saw about subsidence inversion. As the air masses are subsiding in the higher pressure belts, it stifles the rain making process. It obstructs the rain forming process in the higher altitudes. Sorry, in the high pressure belt region, especially along the 30-degree latitudes. Okay, so these are certain significances of temperature inversion. They all are given in the handout. You can go through them. You can mug it if you want. These are the significances of temperature inversion. Okay. Now let's move ahead. This will be provided to you, so don't worry. You can mug it or make your notes from these things. Okay. Now let's move to the last part, that is the concept of atmospheric stability and instability. Now we will be looking into the last concept of temperature inversion. It is related to temperature inversion, the concept of atmospheric stability and instability. Atmospheric stability and instability. The air mass without any vertical movement, either upward or downward, is known as the stable air mass, whereas the air mass where there is vertical movement, either upward or downward, it is known as the unstable air mass. The stability and the instability of this air mass with respect to the atmosphere surrounding it, it depends on the relationship between the normal lapse rate and the adiabatic change of temperature of the air mass. We all have studied about the normal lapse rate a while ago. You all are aware about the normal lapse rate. Anyone would like to explain? Alok? No? Krishna? The decrease in temperature, it is the rate of decrease in temperature, the average rate of decrease in temperature with increase in altitude is referred to as the normal lapse rate. Okay, so the concept of atmospheric stability and instability, it it is an interrelationship between the normal lapse rate and the adiabatic change of temperature of the air mass. Now let's try to understand this concept with the help of diagram. Okay, the adiabatic change of temperature takes place either due to the expansion of the air mass or due to the contraction of the air mass. If there is contraction, the temperature will rise. As the molecules of the air masses, they are clubbed together, the temperature will rise. If it is expanding, then there will be loss of heat and ultimately cooling will occur, thus resulting into decrease in temperature. Fine. Now let's understand the concept of atmospheric stability. Suppose there's an air mass, it is having a dry adiabatic lapse rate higher than the normal lapse rate of the surrounding. Let's say its lapse rate is 10 degrees Celsius per kilometer. This is the ground surface. Its temperature is, let's say, 40 degrees Celsius. The ground surface temperature is around 40 degrees Celsius, and the dry adiabatic lapse rate of this air mass is around 10 degrees Celsius per kilometer. Now, after this air mass, after reaching a certain height, say about 1 kilometer, the temperature of this air mass will be how much? It will be around 30 degrees Celsius. Okay. And the normal lapse rate of the surrounding is, say, let's say around 6.5 degree Celsius per kilometer. So the surrounding temperature at a height of around 1 kilometer, it will be 33.5 degree Celsius. So if we compare these two, the temperature of this air mass as 30 degrees Celsius and that of the surrounding is 33.5 degrees Celsius. Now, since this air mass is much cooler as compared to the surrounding environment, what happens? It being cool, it becomes stable over here. It does not expand and rise further above this particular layer. As a result, a stability is observed in the rising of this particular air mass, and here the stability of atmosphere will be found. Okay, I hope this is clear. Since the dry adiabatic lapse rate of the air rising air mass is higher than the normal lapse rate of the surrounding environment, the air mass after reaching a particular height, it becomes stable. It is not either able to move higher nor it will immediately subside. Okay, try to understand this. Now most of you will be confused over here that the temperature of this air mass is less as compared to the surrounding environment. Now since it is cold, it should become heavy and it should descend, but this phenomena, it will descend but not immediately. A stability in the atmosphere will be observed for a certain period of time. As we all know, the weather, the climate phenomena, they all are highly dynamic. Okay, but there will be stability for some time. For example, we see in the spring season, in the autumn season, the temperature and the atmospheric stability, there won't be any clouds as such in the atmosphere. There will be clear sky and the temperature, the weather will be quite pleasant. Okay, so it all occurs because of the atmospheric stability. A stable atmosphere is observed during spring and autumn season. Okay, now let's understand the instability. Suppose the temperature of this rising air mass is less than that of the normal lapse rate of the surrounding environment. Let's say it's around 10 degrees Celsius per kilometer only, and that of the surrounding environmental air mass is around 11 degrees Celsius per kilometer. Now, what happens is at a height of about 1 kilometer, this will be again 30 degrees Celsius, but the surrounding environment, it will be 29 degree Celsius. Now since the temperature of the rising air mass, it is still higher than the surrounding temperature, it will continue to rise. It will continue to rise and expand, thus causing atmospheric instability. As we have seen in the definition, the vertical movement of the air masses, if it is continuing, it leads to atmospheric instability. It will again rise above up to a certain height. Okay, so that's it regarding the atmospheric stability and instability. If you have any doubts, queries, you may ask. It's fine. Anyone? So that's it about atmospheric stability and instability. So I'll just summarize the entire temperature inversion. First of all, we saw the definition, normal lapse rate and temperature inversion. The second, we saw the types of temperature inversion, basically two types, the surface inversion and the upper air inversion. Then we saw the subtypes of each of these two. The subtypes of surface inversion are the radiation inversion, the air drainage inversion, and the advection inversion. Okay, we saw all those three in detail. Then the subtypes of upper air inversion. The first one was the subsidence inversion. We also saw the concept of trade wind inversion, which is related to subsidence inversion, which mostly takes place in the tropical region from 10 to 30 degree latitudes. Then we saw the frontal inversion, the second subtype of the upper air inversion. Later on, we moved on to the significance, which is provided in your notes. You can go through it. And the final part, the concept of atmospheric stability and instability. I hope this all these concepts are clear to every one of you. Fine. So that's it from my end. Thank you.